Welcome to the video lecture series for Texas A&M University Course Math 152. Today we will take a look at section 10.6, Functions as Power Series. You can find the accompanying handouts at bit.ly/Raelene Math 152. Let's begin. For our brief warm-up, consider in number 1 that f of x is the function 1 over 1 minus x. Let's express f as the sum of a geometric power series, expressed as the sum of coefficients Cn times powers of x minus a. And so here we are going to say, if we recognize this as the sum of a geometric series, then we know that the sum of a geometric series is a over 1 minus r, which must equal 1 over 1 minus x. So our geometric series says that a is equal to 1 and r equals x, which must be contained between -1 and 1 for convergence. We, of course, only have the sum if we have convergence of the geometric series. So we are going to rewrite the sum, or f of x, in expanded form as the first term 1 plus 1 times the common ratio x multiplied by the common ratio, etc. And we can generalize this to get the summation notation from n equals 0 to infinity of powers of x, namely x to the n. So in part B, we know that convergence of the geometric series, in order to get the sum, implies that r, which is equal to x, must be contained from -1 to 1. And therefore I is x contained from -1 to 1. In part C, we want to sketch the graphs of the nth partial sums, Sn, for n equals 1. Well, in fact, let's make that include a 0 as well. 0, 1, 2, 3, 4, 5, and see what happens to the convergence of the partial sums to the infinite or the final exact sum. So we have the function y equals 1 over 1 minus x. As far as being a function in pre-calculus is concerned, we know that it has a vertical asymptote at x equal to 1 and a non-vertical asymptote or horizontal asymptote of the x-axis. Now let's consider the nth partial sums. If we have y equal to 1, we can see that the two functions match only at the center of tangency, or the center of the approximation. Customize this a little bit so we can see the equations as well as the graphs on a smaller window. So we'll save these. And now the next partial sum is y equal to x, 1 plus x, which of course is the tangent line. If we were to zoom in at the point of tangency, we would see that the purple graph and the curve zoom in to look alike. And we'll save this graph. And then if we take x squared, we have the second partial sum. So technically we have the 0th partial sum, the first partial sum, and the second partial sum. I'm trying to make them all about the same size. This is for n equal to 3. And we're finding that we do indeed have different behavior outside of the interval of convergence. Certainly the polynomial is not well matching the blue curve passed on the right-hand side of the vertical asymptote. And we can see there's nice behavior matching here, very closely matching. Again, if we were to zoom in at the center, x equal to 0, we can see that there are more and more x values for which these two curves are matching or converging. And we'll do one last one. In fact, I know I said we'll go up until n equals 5. We'll do that for the 5th degree polynomial. So here n refers to the degree of the polynomial. And we can see that we have even better and better approximations by the polynomial in purple to the nonlinear function in blue. The polynomial is nonlinear as well, but it's nicely behaved. And so we can see that by adding a few more terms of the polynomial, we can get nicer and nicer approximations for more or a wider set of x values, namely the interval of convergence. So let's just focus on the interval of convergence and put that here. And we'll drag the graph down a little bit. And if we zoom in at x equal to 1, and rather x equal to 0, we can see that when x is from maybe about negative 0.4 to 0.4, we have better and better terms. But if we express this in terms of the summation notation, here we're going to change this to x to the k, because k is the index, and let's go maybe to 10 or to 20. We can see that we have an even better and better approximation on a wider width. So let's change that graph. And we can see that the interval of convergence is much, much better now for bigger values of k or n. Let's see how much it likes. It doesn't mind going 200 terms, so we'll use that as our better and better approximation. Okay, so there's kind of a limiting behavior, not as far as we can take k, but it's getting better and better. Okay, so let's move on to the next example. I think that's everything from number 1. In number 2, it says to let f of x equal 1 over 1 minus x, and to determine the following. We have some compositions, we have some products, we have some derivatives and some antiderivatives. So let's just go and work these things out. If we substitute x with negative x, we get 1 minus negative x in the denominator, which gives us 1 over 1 plus x. In part b, we will have x squared times f of 2x, which will give us x squared over 1 minus 2x. In the denominator, we have 1 over 1 minus negative x squared, which is going to be 1 over 1 plus x squared. In number 3, part D, we're going to multiply by 3 and divide by 1 minus the radius of x squared over 2. And f prime, we're going to see if we have f of x is equal to 1 minus x to the exponent of negative 1, then the derivative is going to be negative 1 times 1 minus x to the exponent negative 2 times negative 1 by the chain rule, which gives us 1 over 1 minus x quantity squared. In part f, the antiderivative is going to give us the integral from a to t of 1 over 1 minus x. I'm going to write that as x minus 1, and I'm going to change the sign overall, which means I could swap the bounds and ignore that negative sign. And so the antiderivative here will be ln of absolute value of x minus 1, evaluated from t to a, which is going to give us the ln of absolute value of a minus 1 minus the ln of absolute value of t minus 1. In part G, the domain of f is simply x contained in the reals but not equal to 1, because that's an x value that makes y undefined and therefore has a vertical asymptote on the graph of f. The domain of f prime is also x not equal to 1, so it's the same as the domain of f. And the domain of G, we see that t is not allowed to equal 1 because we would end up having a vertical asymptote. In other words, we'd have the ln of 0, which is undefined, so a vertical asymptote. However, t could be negative numbers because of the absolute value. So we have the same thing, all reals for x or for t, except for 1. Now, of course, we would have to choose the constant a so that it's not equal to 1 as well, but this would be already determined by the question. In number 3, determine a power series and interval of convergence for 3 times f of x squared over 2. Well, if we have this function, 3 times f of x squared over 2, we can see it as another geometric power series, but this time we have a different a value and a different r value. So we can see that this is the sum of a convergent geometric power series with a equal to 3 and r equal to x squared over 2, as long as, to be convergent, r which equals x is contained, r which is equal to x squared over 2 is contained from negative 1 to 1. So the power series is going to be plus 3 times x squared over 2 plus 3 times x squared over 2 all squared plus dot dot dot, which can be written in summation notation as the sum from n equals 0 to infinity of 3 times x squared over 2 to the exponent n, and the interval of convergence is going to be that negative 1 is less than x squared over 2, which is less than 1. And from here we can multiply all sides of the compound inequality by 2 to get negative 2 is less than x squared, which is less than 2. And now solving graphically, we require that the graph of x squared be bounded between the horizontal lines of y equal to negative 2 and y equal to positive 2. And we see that that occurs for the boundary values of negative root 2 to positive root 2. And so the interval of convergence is going to be x contained on the interval from negative root 2 to positive root 2, which of course has nothing to do with taking the square root of all 3 sides. This is not correct. We are not allowed to do this. Specifically, we can note that the square root of negative 2 does not equal the negative square root of 2. And so please be careful that you are solving graphically when you have nonlinear inequalities. Moving on to number 4, consider the function y equals tan inverse of x. Evaluate tan inverse of x. If you're not sure how to do that, you may want to think graphically, and the graph that many students are more comfortable with is the regular trig function as opposed to the inverse trig function. There are vertical asymptotes when the cosine graph has zeros, namely at the odd pi by 2's. And the graph of tangent is increasing for each branch. And of course, the zeros of tangent are the same as the zeros of sine x. From here, we restrict the domain so that the function becomes 1 to 1, and then we reflect through the line y equals x, so we can come up with the graph of tangent inverse. So the vertical asymptotes on the principal or the restricted branch of the tangent graph become horizontal asymptotes of y equal to root pi by 2 and negative pi by 2 for the inverse function. And our tan inverse graph looks like this, and when x is equal to 0, y is equal to 0. So tan inverse of 0 equals 0. Now we want to express tan inverse of x as a definite integral of another function. So we know that we can express any function. Let's use the fundamental theorem of calculus, and let's say that the function is g double prime of x. We can express that as a definite integral from a to x of the derivative of g double prime, namely g triple prime of some other variable t dt. So from here we can state that tan inverse of x minus tan inverse of 0 is going to be, actually let's be really clear, I didn't write this correctly in the first part. Let me erase all of this, I guess. I'll erase this. And we know that g double prime of x minus g double prime of a is given by the fundamental theorem of calculus, the evaluation part. And so tan inverse of x minus tan inverse of 0 is equal to the definite integral from 0 to x, because we know that this is the input and this is the output. So here we have the input value, a is equal to 0. And then the derivative of tan inverse of x is 1 over 1 plus x squared. But we can't use x here because we can't substitute x into itself. So we use a different variable, 1 over 1 plus t squared dt. And of course, tan inverse of 0 is 0. And so we can express that tan inverse of x is equal to the definite integral from 0 to x of 1 over 1 plus t squared dt. Now let's consider representing functions as power series. We have seen that a basic geometric power series is given by 1 over 1 minus x, which is geometric and convergent as long as x is contained from -1 to 1. So now that we have one basic power series, we can perform some composition, f of g of x, to algebraically determine or create new power series. So the resulting series will be a geometric series with r equal to the inner function. If we perform a composition, f of g of x is going to look like 1 over 1 minus g of x. And therefore r is equal to g of x, which has to be contained from -1 to 1 in order for this sum of a convergent geometric series to exist. Furthermore, we may have other kinds of combinations. 3 times f of x would give us 3 over 1 minus x, and therefore r is still equal to x, but we would have a equal to 3. Or we could do a combination x squared f of g of x, which would not just change r and not just change a, it would change both. So we would get x squared over 1 minus g of x, and we can see that r is equal to g of x, and a is equal to x squared. So we can do different combinations of algebraic functions. We can add, subtract, multiply, and divide them, and we can compose them to create new power series. But of course, we would have to come up with the new interval of convergence. So let's take a look at doing this on a few different examples. Number 5a asks, on what interval does each of the series below converge, and to what? Well, the first power series has a equal to 1 and g equal to r, r equal to x. So this is going to be a geometric power series of f of x equals a over 1 minus r equals 1 over 1 minus x, where r equal to x is contained from -1 to 1. That is our basic one. We can memorize this. In this case, we see that a is equal to 1 and r is equal to x minus 1. So we have f of x minus 1, or simply f of x, or we can call it y or g of x, or we could just let this be s for the sum of the series. So s is equal to a over 1 minus r, which is 1 over 1 minus x minus 1. And when we expand this carefully, we get 1 minus x plus 1, which is going to be 1 over 2 minus x. And now we want to know the interval of convergence. So we know that x minus 1 must be between -1 and 1. And we can simply add 1 to all sides, and we get that the interval of convergence is x contained from 0 to 2. So we have the series, the sum rather, and we have the interval of convergence. What this tells us then is if we were to look at the polynomial, the finite polynomial, adding more and more terms would approximate or approach the sum 1 over 2 minus x on the interval of convergence 0 to 2. Try it on a graphing program, as we did earlier in number 1, to check for yourself. In part C, we see that we have a geometric series with a equal to 1 and r equal to x squared, which must be contained between -1 and 1. And so therefore the sum is going to equal 1 over 1 minus x squared, where x is going to be between -1 and 1. We see If we have 1 here and negative 1 here, our solution is only to do with this portion of the graph. And so x is from negative 1 to 1 exclusive. So the interval of convergence is going to be given by x contained from negative 1 to 1. It's just a coincidence that they're the same numbers. Please make sure that you solve the nonlinear inequality graphically. In the next case, we see that we have a equal to 1 and r equal to x minus 3 over 2. And so the sum is going to equal 1 over 1 minus x minus 3 all over 2. And we can simplify this by multiplying the top and the bottom by 2. If we do that, we get 2 times, multiply here by 2, we get 2 minus x plus 3. So 2 minus x plus 3 is 5 minus x. And so this is a simplification of the sum. From here we see that x minus 3 all over 2 must be contained between negative 1 and 1. And therefore negative 2 must be less than x minus 3, which must be less than 2. And therefore the interval of convergence is x contained from 1 until 5. You should try graphing all of these polynomials with more and more terms, so a sequence of partial sums of the series, and you should also check with the function or the sum expression 1a over 1 minus r on the interval of convergence. In number 6 then, determine a power series that represents the following functions and determine the interval of convergence for each. Well, let's contrast number 6 with number 5. In number 6, we're given the result of a over 1 minus r, and in number 5, we are given the expanded series so that we have to determine a and r and come up with the expression a over 1 minus r. Okay, so if we do this, in part A, we see that we have a is equal to 1, and r is equal to negative x. So the power series is going to be 1 minus x plus x squared minus x cubed plus x to the 4 plus dot 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 plus x to the n. Well, we have to be careful because the term could be positive or negative. So we see that the series is alternating, and we write the sum from n equals 0 to infinity. We have negative 1 to some exponent and then x to the n. So when the exponent is an even exponent, 0, 2, 4, we have a positive. And since we're beginning the sum at n equal to 0, we can put an exponent of n here to start off with a positive 1. And now the interval of convergence, we require that r, which is x, is contained from negative 1 to 1, and therefore the interval of convergence is simply still x contained from negative 1 to 1. In part B, we're doing something very similar as part A, except we're taking the sum from part A and we're multiplying by x. So we have a equals x, and r is equal to negative x. And so if we just take our result from part B, from part A into part B, this new sum is going to be the previous sum multiplied by x, because we're multiplying 1 over x times 1 over 1 plus x is being multiplied by x. And 1 over 1 plus x is the result from part A. So we're going to get x times 1 minus x plus x squared minus x cubed plus dot dot dot, which equals x times the sum from n equals 0 to infinity of negative 1 to the n times x to the n, which we can rewrite by taking the x constant with respect to the summation inside, and we get the sum from n equals 0 to infinity of negative 1 to the n times x to the exponent n plus 1. And we know that the interval of convergence is still for r, which is negative x, to be contained from negative 1. Therefore, the interval of convergence is still x contained from negative 1 to 1. Okay, for part C, we can see that there's a different r value here. If we just state r value, we'll leave part C to be done as an exercise. We see that a is equal to 1, and we see that r is equal to positive 2x. And then in part D, we can see that 1 over x needs to be cleverly rewritten in the form of a over 1 minus r, and we do that by recognizing that we have x is the same as 1 plus x minus 1. If we drop the brackets, we get 1 minus 1 is 0. But then we need to write this as 1 minus something. So we are going to rewrite part D as 1 over 1 minus the negative of x minus 1, namely 1 minus x. And so in part D, a is equal to 1 and r is equal to 1 minus x. And then in part E, we can see that this is 1/3 times 1 over x, which is the expression that we had found in part D. So we do have to get a little bit creative with the algebra in order to see the form of a over 1 minus r every time. And then we're doing some kind of algebraic combination by multiplying, dividing, composition, for example. And so we can take the sum from 1 over x from part D, multiply by 1/3, and get the answer for part A. So do finish parts C, D, and E, and check your answers with the completed lecture notes. Now we're going to move on to beyond algebraic combinations or compositions of basic power series, and we are going to consider differentiating or integrating power series. As we saw in the warm-up, we had a function f of x, we were able to take its derivative, and we were able to take its antiderivative. It maintained the same domain in each case, and of course, if a function f of x has a power series, then the power series is an infinite polynomial, and all of the polynomial derivatives or antiderivatives will exist. So given that a power series for a function f of x exists, and it has a certain interval of convergence, let's say r spaces to the left and to the right of the x-coordinate of the center. Remember, we would have to have that x minus a has to be less than r, implies that a is the center, and we go the radius of convergence distance to the left and to the right, taking us to a minus r or a plus r, and x has to be inside that interval in order for the series to converge. So then, if f of x is given by a polynomial, we can take the derivative of every term on the right-hand side. So f prime is going to be 0 plus c1 times 1 plus 2 times c2 times x minus a to the 1 plus 3 times c3 times x minus a to the 2. In general, the n will come down and be n times cn times x minus a to the exponent of n minus 1. So we will have the derivative given this way. We can also take the antiderivative between x naught and x, which is going to give us some antiderivative function f of x minus f of x0. And depending on what we choose for x0, we get a specific constant of integration here, because we can take f of x0 to the other side. And so what's happening is that we're going to get the antiderivative of every term here. So keep in mind again that we would have started off this series with 0 plus c1, and the antiderivative of 0 is some constant called c. And then we have the c naught, rather, I'm starting in the wrong place. If I start from the f of x, we had 0 plus c naught, so the antiderivative of 0 is c. The antiderivative of the constant c naught is c naught times x minus a. The antiderivative of c1 x minus a is c1 over 2 times x minus a squared, because we increase the exponent by 1 and divide by the new exponent, and so on for each term. So we add 1 to the exponent and divide by the new exponent. But we also have this constant of integration c, which we will put as a capital C at the very beginning. Okay, well, what's happening is that the polynomials are all, the terms of each polynomial for the function, the derivative, and the antiderivative are all centered around x equal to a. And therefore, the polynomials, in terms of the powers of x minus a, all have the same domain restrictions. In other words, all three of these functions will have the same interval of convergence from a minus r to a plus r. Let's take a look at an example in number 7. Determine a power series that represents 1 over 1 minus x all squared, and then determine the interval of convergence and the radius of convergence. Well, this function, 1 over 1 minus x all squared, can't, or at least right now, it's not so easy to express in the form of a over 1 minus r. And so we are not prepared to see this as an algebraic combination or composition of a basic power series with some other inner function. So what we need to do is recognize 1 over 1 minus x all squared in a different way. That doesn't involve algebraic. So what we can see is 1 over 1 minus x all squared is the same as 1 minus x to the exponent of negative 2, which may remind us of having taken the derivative of 1 over 1 minus x. Now 1 over 1 minus x does have the form of a over 1 minus r. And as a result, we can recall that 1 over 1 minus x is the basic power series, the basic geometric power series, with an interval of convergence of x contained from negative 1 to 1. And so as a result, if we want to get 1 over 1 minus x all squared, then we can take the derivative of 1 over 1 minus x, and we can substitute 1 over 1 minus x with the power series or infinite polynomial of 1 plus x squared plus x cubed, etc. But what's happening as soon as we take the derivative of this? We notice that we are going to get 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot. We could have written the general term here, but we will write the summation fine at the end. But we notice that as far as being a power series, this is still a power series because we still have coefficients and powers of x minus 0 because we have a center here of x equal to 0. But we no longer have a geometric series because if we have a geometric power series, then we recall that all of the coefficients must be the same. So we can see that we're multiplying by x from one term to the next. But we don't have a common ratio because 2x over 1 does not equal 3x squared over 2x. So in fact, we do not have a geometric series any longer because the coefficients are constant, which means that we don't really have a common ratio of x. From this first non-zero term to the second, we multiply by 2x, and then we multiply by 3 over 2x, and then we multiply by 4 over 3x. And so because the coefficients are not constant, we don't have a geometric series any longer. So as soon as we take the derivative of a geometric power series, the result is no longer geometric because the constants are not equal. Okay, no problem. We still have a power series, and we are going to represent this in summation notation. So we have the sum from n equals 0 to infinity, and the coefficients are 1 less than the exponent, so we're going to have n times x to the n minus 1, and if we write this with n minus 1, we need to start the series from n equal to 1. We could see that as the derivative as the power series that we started off with from n equals 0 to infinity of x to the n. If we bring down the exponent, we have n times x to the n minus 1, and we would have gotten the first term here with n equal to 0, or we could start on the first non-zero term. So it doesn't really matter which way we write the series. It will either include the 0 in the expansion if we use this green version, or it will start from 1 if we use the red n equal to 1 version. Okay, well the nice thing is, although we no longer have a geometric series, we do still have the same interval of convergence. So the interval of convergence is still for x contained from negative 1 to 1. And therefore the radius of convergence, if we take a look at this as an interval along the x-axis from negative 1 to 1, and that's kind of like a circle, except it's the projection on the x-axis, we see that the radius is equal to 1, whether or not the endpoints are included. In number 8, let's consider f of x to be ln of 1 plus x. We are asked in A to integrate a basic power series to determine a power series for f. So we need to see some recognition or connection between a basic power series that we can write in the form of a over 1 minus r to the function ln of 1 plus x. So to get started, let's just consider if y is equal to the ln of 1 plus x, what is its derivative? The derivative will be 1 over 1 plus x, which is a power series when we express this as, it's the sum of a power series, which is geometric, when we express the denominator as 1 minus negative x. And so we can see that with a equal to 1 and r equal to negative x, we could have y prime equal to 1 minus x plus x squared minus x cubed plus dot dot dot, which is equal to the series from n equals 0 to infinity of negative 1 to the n times x to the n. And so from here, we want to take the antiderivative to get the ln of 1 plus x. So the ln of 1 plus x is going to be the antiderivative of 1 over 1 plus x dx, which is the antiderivative of 1 minus x plus x squared minus x cubed, etc., with respect to x, or the antiderivative of the series from n equals 0 to infinity of negative 1 to the n times x to the n, and then dx. Well, let's focus on the expanded version. When we're taking the antiderivative, we are going to get x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, and the presence of the denominators 2, 3, 4, etc. remind us that the antiderivative of a basic geometric power series is no longer geometric because we do not have constant coefficients. And then we get plus dot dot dot, but every time we take the antiderivative of the antiderivative for an indefinite integral, we get a constant of integration plus c. And so we can write this in sigma notation as c plus the sum from n equals 1 to infinity of x to the n over n. Okay, so that's part A. In part B, it says to use technology to graph a sequence of partial sums to see how these better and better approximate the graph of y equals ln of 1 plus x. So let's take a look at the graphs of y equals the ln of 1 plus x. And we see there's the graph of ln x, translated 1 back. We could also write this as x plus 1. And now we have y equals x. We have y plus x squared over 2. Rather, it should be minus because we have alternating series here. Let's just double check our signs. Okay, so then we have the third term is plus x cubed over 3. And we can see that we do have more and more of the polynomial graph approximating or converging to the blue graph. Then we have minus x to the 4 over 4, and even more. And if we were to write this in sigma notation, we could take the sum from k or n equal to 1 from 1 to 5 of negative 1 to the exponent k, except we have to start off with k plus 1 now, and then multiplied by x raised to the k over k. And so we can see if we turn this to k equals 4, up to 4, we see that the purple is the same as the red. So now I'm going to turn off the purple one so that we can use the sigma notation to write these terms faster. And so if we go up to 10 or to 100, we don't see that the red graph is seeming to go beyond a certain interval of convergence. For one, we know that there is a domain restriction on the original function that x cannot be less than negative 1, and we don't see our polynomials in red matching beyond that. If we expand, we see that there's a difference between the red and the purple and the blue graphs when x is less than negative 1. Certainly x is allowed to be -1 in the polynomial, but x is not allowed to be -1 or less in the blue function. So this is suggesting that the -1 x value is a left limit on the interval of convergence. But we can also see that the two blue and red graphs do not converge when x is greater than 1. So this suggests that we have an interval of convergence -1 less than x less than 1. And sure enough, that seems to do the trick. So in part B, it says to use technology to graph a sequence of partial sums, and we can conjecture that the interval of convergence is from -1 to 1. Well, we know that that will be the case because in part A, we had the series 1 over 1 plus x given by 1 minus x plus x squared minus x cubed, etc., with an interval of convergence of x contained from -1 to 1. And therefore, the antiderivative of this, which is ln of 1 plus x, which has the power series of the antiderivative of each term, will have the same interval of convergence. And now in part C, it says to approximate the ln of 2 and the ln of 3 using a 4th degree power series. And we want to compare with the TI values. And are these values very meaningful? Why or why not? Well, if we take a look in part C at the ln of 2, we know that it has to be the ln of 1 plus 1. So we are taking our function f of x equal to ln of 1 plus x, and we are substituting x equal to 1. And so if we take the power series, it is no longer a geometric power series. We can simplify, or substitute rather, x equal to 1 into the 4th degree power series. So let's call this f subscript 4 for the 4th degree power series. And then f subscript 4 evaluated at 1 is 1 minus a half plus 1 cubed minus 1/4. And we get a value compared with the ln of 2. So let's just take a look on a calculator to see how well that looks. So if we take a look on the TI, we can approximate the ln of 2 to be 0.693147118, etc., etc. Then let's take a look at the power series. We can write it from n equals 1 to 4 of -1 to the exponent n plus 1 times x, this is going to be a fraction. We can put n down there, we need still x up here, x to the exponent of n. And so, well, let's change this. This should not be in the exponent. We've got, rewriting this, we have x raised to the n. Okay, so there is our 4th degree polynomial, and if we approximate that or evaluate that, when x is equal to 1, I'm going to put 1.0 so I can get a decimal. I see that my two values are not even correct in the first decimal place, so this is not very good accuracy. Well, we could try the same thing with the ln of 3, but in using the ln of 3, we need to substitute x with 2 this time. So this is equal to, approximately equal to 0.58333, and the ln of 2 is approximately 0.6, what was it, 693? So not very close. We're not very accurate. Similarly, if we repeat the process for the ln of 3, that's saying ln of 1 plus 2, and therefore we are looking at f of 2, which is approximately ln of 3 is approximately 1.09861. Meanwhile, f subscript 4 of 2 is going to be 2 minus 2 squared over 2 plus 2 cubed over 3 minus 2 to the 4 over 4, which approximates as a decimal to be negative 1.333. That's an even worse approximation. We don't even have the same y value, the same y sign. The output signs are different. Negative 333, etc. And so we're seeing that these are even worse approximations. And the reason for that, if we go back and we take a look at the graphs, we see that when x is beyond negative 1 to 1, specifically when x is 2 or 1, that the red polynomial values are starting to diverge from the blue exact function values. And so we cannot use the red polynomial as an approximation to the blue curve outside of the interval of convergence. Okay, then in part D it says, how could we improve the approximation to ln 2? Well, ln 2 isn't going to get any better really unless we take more and more terms, but then we'd have to wonder, is x equal to positive 1 in the interval of convergence or not? And so what that really means is we would have to take a look at the power series at the endpoints, because maybe x equal to 1 actually should be included in the interval of convergence. So let's go ahead and write down our power series for the ln of 1 plus x, which we said is the sum from n equals 0 to infinity of negative 1, rather n equals 1, to infinity from of negative 1 to the n plus 1 times x to the n over n. And so if we substitute x equal to 1, does this series converge? So we need to ask that question. Does the series converge when x equals positive 1? Well, we've done this before. We can substitute x equal to 1 in, and therefore we get the series from n equals 1 to infinity of negative 1 to the n plus 1 times 1 to the n, which is 1, over n. And this series is none other than the alternating harmonic series. So let's just expand a few terms. When n equals 1, we get negative 1 squared is 1 over 1. Then we get minus 1/2 plus 1/3 minus 1/4, etc. is the convergent alternating harmonic series. So therefore, the interval of convergence for the ln of 1 plus x power series is x contained from negative 1, not included, up to and including 1. Which means that this series should and will converge to the ln of 2 when x is equal to 1. So how do we make that a better and better approximation? We weren't so far off. We had 0.58333 and 0.693. But maybe 4 terms, or the 4th degree polynomial, wasn't big enough. So if we take more and more terms, we should be able to improve the approximation of f sub 4 of 1 to the ln of 2. So let's try a few more terms. And if we go here, evaluated when x is 1, what we're really doing is evaluating the alternating harmonic series. And let's approximate this with 1.0 so we get a decimal every time. And 1.0 to the n is still 1.0, so we get 0.6453. If we take more terms, 100, then we get 0.688. Let's just remind ourselves what the ln of 2 is approximately equal to. Okay, so we need a few more terms, maybe take 1,000 terms. And we're starting to get, the first 2 decimal places are the same. Maybe if we take 10,000 terms, this is taking a long time, we start to get, still only accurate, well, let's put the ln of 2 in again. We're starting to get accurate to the first 3 decimal places. So we are accurate to within the first 3 decimal places, or 10 to the negative 4. Well, it's taking many, many, many terms to do so because the alternating harmonic series is not absolutely convergent, which means that it is very slow to converge. It takes a lot of terms for this to converge to the exact value. However, it is converging, just very, very slowly. Okay, so then let's take a look at the last part. What is wrong with the approximation to the ln of 3? Well, we know that from the graph for ln of 3, that means that x is equal to 2. And the x equal to 2 value is far outside the interval of convergence. X equal to 1 was included, and so we were able to get some convergence there, but x equal to 2 is not convergent for this series. And so we are not going to be able to take more and more terms when x is 2 and get the red heights to match the blue heights. What we can do, however, is shift the center. If we really wanted to evaluate or approximate the ln of 3, we would have to translate the power series to the right, and then we would be able to change the interval of convergence from -1 to 1, from 0 to 2, or even from 1 to 3. But that would require us translating the x-coordinates, or replacing every x with x minus 1 to move 1 space to the right, or x minus 2 to move 2 spaces to the right, and therefore put 2 at the center of the interval of convergence. If we did that here, though, and replaced x with x minus 1, we would have to replace this x with x minus 1 as well. Moving on to number 9, let's determine a power series in the interval of convergence for tan inverse of x. Well, again, we need to think of tan inverse of x as the derivative or the integral of a basic geometric power series, because tan inverse of x is not in the form of a over 1 minus r. But we do know that the derivative of tan inverse of x is given by 1 over 1 plus x squared, which does have the form of a over 1 minus r, where a is equal to 1 and r is equal to negative x squared. And so we can take the derivative of tan inverse to get the power series, or we could switch this to say that tan inverse of x is the antiderivative of 1 over 1 plus x squared dx. So the expansion for 1 over 1 plus x squared dx is going to be a equal to 1 times the r value for the next term, times the r value, times the r value, etc. And so here when we integrate, we get x minus x cubed over 3, and all of a sudden we can see that we do not have a common ratio any longer, and so the integral of this geometric power series is no longer still geometric. So we've got unconstant or non-constant coefficients, so we do not have a common ratio. And then, of course, for an indefinite integral, we have plus c. We could have written this in a different way by saying that tan inverse of x could be expressed as a definite integral. We could say that tan inverse of x minus tan inverse of 0 from the fundamental theorem of calculus can be expressed as the integral from 0 to x of 1 over 1 plus t squared dt. And from here, when we integrate on the right-hand side and substitute or replace tan inverse of 0 with 0, we get that tan inverse of x is the definite integral of 1 over 1 plus t squared dt, which is going to be t minus t cubed over 3 plus t to the 5 over 5 minus etc., evaluated from 0 to x, is going to give us the antiderivative function f at x minus f at 0. Every time we substitute this expression with t equal to 0, we're going to get a 0 here. And so we end up with tan inverse of x is simply x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7, etc. So we have our power series, and we want to come up with the interval of convergence for tan x. which will have, tan inverse of x, which is the same interval of convergence as the 1 over 1 plus x squared power series. So the interval of convergence for the power series 1 over 1 plus x squared means that r, which is equal to negative x squared, must be contained from negative 1 to 1. And therefore, negative 1 has to be less than negative x squared, which has to be less than 1. So solving graphically, we draw the graph of the parabola y equals negative x squared, and the two horizontal lines, y equal to 1 and y equal to negative 1. And we see that we don't have any intersection between the blue curve and the red curve, and so we need the red curve to be bounded by the black curve and touching, or not touching rather, the green curve. So we are not going to include the endpoints, and we end up getting the intersection points between the red and the green are at x equals negative 1 or 1. And so the interval of convergence is going to be given by x contained from negative 1 to 1. Again, be careful that you're not simply taking the square root of all sides of the compound inequality, because we would have non-real results, and it's just a coincidence that it looks like the negative comes out of the square root, but that is not what's happening. And so we have the interval of convergence for tan inverse of x, for the power series for tan inverse of x, so its power series is also x contained from negative 1 to 1. In number 10, determine a power series for for the integral from 1 over 1 plus x cubed dx, and determine the interval of convergence, and then use the result to approximate the definite integral of the same function from 0 to 0.1 to within 10 to the negative 9. Well, we are now starting to see one of the applications of power series. We cannot integrate 1 over 1 plus x cubed using substitution, integration by parts, or partial fraction decomposition, trig substitution, etc. But what we can do is represent 1 over 1 plus x cubed by its power series on its interval of convergence. And then we can integrate the power series. So, coming up with an alternative representation of 1 over 1 plus x cubed means that we have to identify a and r. And in this case, we see that a is equal to 1 and r is equal to negative x cubed. So in the expansion, we get 1 minus x cubed plus x to the 6 minus x to the 9 plus dot 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 on the interval of convergence for negative x cubed contained from negative 1 to 1. Thinking and solving graphically, we have the negative x cubed graph like this, and bounding between the curves y equals positive 1 and y equals negative 1, but not equal to the endpoints, we end up getting that x is also bounded from negative 1 to positive 1. Now we are ready to take the antiderivative of the power series and come up with the power series for the given function. Let's call this given function g of x. So therefore g of x is going to be the antiderivative, or the integral, of 1 minus x cubed plus x to the 6 minus x to the 9, etc. And so we are going to get a constant of integration, and then plus x minus x to the 4 over 4 plus x to the 7 over 7 minus x to the 10 over 10, etc. Now we could have seen the nth general term here as alternating in sign, so negative 1 to the exponent of n or n plus 1, depending on how we set up the summation bounds. And then we're going to have times x to the exponent 3n. And so when we add 1 and divide to the exponent and divide by the new exponent, we end up getting an nth general term here of negative 1 to the n times x to the 3n plus 1 divided by the new exponent of 3n plus 1. Okay, so what do we want to do next? We have our power series and we have the interval of convergence, where x is contained from -1 to 1. We now want to use this function, this power series, to evaluate the definite integral from 0 to 0.1 of 1 over 1 plus x cubed dx. Well, if we do that, we know that the definite integral from 0 to 0.1, both x values are within the interval of convergence, and we're going to get some antiderivative function plus the constant, so we're going to get, let's call all of this thing here, let's call that f of x. So we are going to get c plus f evaluated at 0.1. And then we are going to get minus c plus f evaluated at the lower bound. And this is by the fundamental theorem of calculus. So we can see that this c minus c will cancel. And we also know that f of 0 will be 0 minus 0 to the 4 over 4 plus 0 to the 7 over 7 minus 0 plus 0. And so this term will only be 0. So this is the same as saying the f expression evaluated at 0.1. Well, the f expression is x minus x to the 4 over 4, etc. And so this is going to be the same as f of 1/10. And so we are going to get 1/10 minus 1/10 to the 4 over 4, which is 1 over 4 times 10 to the 4, plus 1/10 to the 7 over 7, which is 1 over 7 times 10 to the 7, minus 1 over 10 times 10 to the 10, plus etc. And at this point, we want to come up with the number of terms. We want to approximate the result within 10 to the -9, which means we need to know how many terms to take to be within this accuracy. Well, this accuracy is telling us about the size of the error. So this is an upper bound on the Rn error value. So from here, we need to find what value of n do we take, which means we need an estimate for the Rn. Well, we are lucky to note that this series is alternating. So as long as the terms of the series, the -1 to the n, x to the 3n plus 1 over 3n plus 1, when x is 1/10, if this is a term that satisfies the three conditions for the alternating series test, then we are allowed to use the alternating series error estimate. Namely, the next term after our sequence of partial sums can be the upper bound on the error estimate. So let's just confirm quickly that this series, when x is equal to 1/10, actually satisfies the criteria or conditions for the alternating series test. So our series is 1/10 minus 1 over 4 times 10 to the 4 plus 1 over 4 times 10 to the 7 minus 1 over 10, sorry, that should be 7 here. 1 over 10 times 10 to the 10 plus ... So the general term is -1 to the n plus 1 times 1/10 for x to the 3n plus 1 over 3n plus 1. Actually, I think we're starting at, if we start here at n equals 0, we're going to start at n equals 0, so this is just n plus 1. So we know, therefore, that Bn, this is our an term, so Bn is equal to 1/10 times this, so we're going to get 1 over 3n plus 1 times 10 to the 3n plus 1. This is specifically once x has been substituted with 1/10. And so the three conditions of the alternating series test require that Bn is always positive. We know that this is true because we have the alternating sign coming from -1 to the n. So I'm just going to write true. Signs alternate. The second condition of the alternating series test is that the series is non-decreasing, Well, we can see that the denominator coefficient as well as the exponent on 10 are increasing, making the denominators bigger and bigger and bigger. So we know that 3n plus 1 times 10 to the 3n plus 1 approaches infinity as, no, let's not write it like that. Let's just simply say the denominators are getting bigger, so we've said it out loud. Bn is going to be purely greater than the later terms, not even equal to. And the third thing we notice, the limit as n approaches infinity of Bn is equal to the limit as n approaches infinity of 1 over 3n plus 1 times 10 to the 3n plus 1, which equals 0. And so therefore, this series satisfies the alternating series test conditions. So the upper bound, therefore the upper bound for the error, s minus Sn, which is equal to Rn, is given by the absolute value of An plus 1. Well, we want An plus 1 in magnitude to be at most 10 to the negative 9. So now what we need to do is solve for n such that the magnitude of An plus 1 is less than or equal to 10 to the negative 9. And so all we need to do is look at some of the terms that we have expanded. We know that the series is given by 1 over, what was our first term? 1 over 10 minus 1 over 4 times 10 to the 4, which is going to be, let's rewrite this with exponential notation, 10 to the negative 4 on the top. So 10 to the negative 4 divided by 4, 10 to the negative 1 for the first term, plus 10 to the negative 7 divided by 7, minus 10 to the negative 10 divided by 10, plus dot dot dot. And we can actually look at this term a little more carefully. And we can see that this term is actually 10 to the negative 11 plus dot dot dot. So if this is the An plus 1 term that we're looking for, this is not less than, this is not going to be bounded above by 10 to the negative 9. This term is too big. This term is bigger than 10 to the negative 9. But this term is smaller than 10 to the negative 9. And so we are going to take this term to be the An plus 1 term. Well, technically An plus 1 involves the negative sign, so this term is the absolute value of An plus 1, which means that we had n equals 1, 2, 3, 4, and we are going to choose An plus 1 is 4, which means that n is equal to 3. So we are going to choose n equal to 3. And if we do that, the question again said to approximate this definite integral to within 10 to the negative 9. So that means that we are going to use the first three terms of the expansion of the power series, 1, 2, 3, and we are going to substitute in the bounds for the definite integral, and we are going to come up with this approximation for the definite integral. Therefore, the integral from 0 to 0.1 of 1 over 1 plus x cubed dx is approximately the first three terms that we had just put a box around. 1 over 10 minus 1 over 4 times 10 to the 4 plus 1 over 7 times 10 to the 7, which we can approximate as a decimal, is accurate to within 10 to the negative 9. The last question, number 11, is an exploration. Given a power series, do some analysis of the function, finding some values, some intercepts, some derivatives, and then see if you can't recognize what, based on the characteristics that the power series has, who this might be a function for. This question is a good foreshadowing for where we are going in section 10.7 when we want to prescribe certain characteristics for a function to create a power series that is not geometric. So up until now we have been focusing on power series that are geometric, but with the differentiation and integration of such power series, we are getting resulting power series that are no longer geometric. Can we use those non-geometric power series to represent other functions in the library of basic functions? So I'll leave you to try number 11 by following through the steps and answering the questions on your own, and we will pick up this question as a warm-up for 10.7. This concludes section 10.6, representing functions as power series. Please make sure that you completed the accompanying handout and that you have prepared a list of clarifying questions about the lecture. That's all for now.